Hello, everybody. So today is June 2nd, and today I'm going to go over another Chemthink. This is the last Chemthink that will be assigned. So the only one that I haven't reviewed yet is the Isotopes Chemthink. So I am going to go to Chemthink. There we go. Okay, I'll sign in as my fake student. Okay, now be careful. Again, the first screen is the wrong screen, so go down in the lower left, click back to go to the main menu, and Isotopes. Here it is. I'm not sure why it says Monday. That says it's done today. I'm going to give you another week to do these Chemthinks, so I'll fix that. Anyway, let's keep going. Okay, Isotopes. You have to do the tutorial first. In this unit, we will continue looking at the internal structure of the atom. So this takes us way back last year when we were talking about the parts of an atom. Let's try zooming in on a piece of pure boron. So boron is element, what is it? Element number 4 or 5? Not sure, but it's only got a few protons, neutrons, and electrons. So once we have reached the atomic level, we can see all the boron atoms seem to look the same. However, some of the atoms are actually slightly different than others. How's that? There are 5 protons in boron, 6 neutrons, 5 electrons in this boron atom. This is boron atom's a little different. It has 5 protons and only 5 neutrons and 5 electrons. They both have 5 protons, but they have different numbers of neutrons, and then they have the same number of electrons. Boron has 5 protons. All boron atoms have 5 protons. If they don't have 5, then it would not be boron, of course. Electrons control the chemical behavior. Since they both have 5 electrons, they should be chemically identical. Neutrons hold the nucleus together. Since the first atom has 1 more neutron than the second, the first is heavier. Remember, it's protons and neutrons have the mass. The electrons are so incredibly smaller, 2,000 times smaller. We ignore the mass. These atoms are isotopes of boron. Isotopes are atoms of the same element, the same number of protons, but different number of neutrons, different mass. And don't confuse isotopes with ions. They both start with I. Isotopes has to do with the number of neutrons. Ions has to do with the number of electrons. These borons are almost identical. The only way to tell them apart is by their mass, how much they weigh. Chemical reactions, the 2 isotopes will act in the same exact way. They're both chemically the same because chemical reactions only involve electrons. They have the same number of electrons, so they behave the same chemically. Nuclear reactions. During nuclear reactions like radioactive decay or fusion, we show the difference by using special symbols, because in nuclear reactions, the changing of the nucleus, where the borons hang out, the borons actually matter. How many neutrons you have actually is important. To distinguish the isotopes, we use isotope symbols like the one shown at the bottom. So here you can see that on the top left of the capital B, the chemical symbol for boron, there's a 10, and that's the mass. It's how many protons plus neutrons. On the bottom left is a 5, and that's the atomic number. We also use letters to indicate these. The top would be an A, and the bottom would be a Z. You'll see that also. The bottom number is the number of protons. This is called the atomic number. And in this case, it's 5 for boron. If it's not 5, it is not boron. It's something else. The top is the number of protons plus neutrons. This is called the mass number. We have other names for it: the atomic mass, the atomic weight. You know, there's various, over the years, there's various names for the top left number. But the modern way that the modern name we generally use is mass number. Okay, fill the correct numbers for the other isotope of boron. Okay, so we know that the bottom, and look how if I hover over the box, there's little arrows here. I can use those to change the number, and it's a 5 because there's 5 protons. That's the atomic number. The top number is 11. Why 11? It's because 5 protons plus 6 neutrons, that's the mass. It's the mass number. Correct. The bottom number, the top number is 11. The bottom number is 5. We also have a way to refer to these that demonstrates the difference between them. Again, the only difference is the mass number. So we put a dash and then the mass number. So for boron with 6 neutrons, it would be dash 11. Boron with 5 neutrons would be dash 10. How do I know there's 6 and 5? Well, 11 minus 5 for the boron 11. 11 minus 5 is 6. That's 6 neutrons, right? Because the bottom is 5 protons. The top is the protons plus the neutrons. So we just subtract the top minus the bottom. That gives us the number of neutrons. Now that we know how the isotopes are different, let's figure out how many of each are in the piece of boron. Okay, so boron 11 and boron 10, that's how we say it, boron 11, boron 10, they're 2 different isotopes of boron, are not present in equal amounts. The sample is approximately 80% boron 11 and 20% boron 10. So that's what that means with this percentage. It means how many in 100. So if you had 100 atoms of boron, 80 of them, 80% would be boron 11. 20 of them, 20% would be boron 10. So it's based on a factor of 10. 100. In fact, all boron samples taken from Earth will have the 2 isotopes in the same amounts. So wherever you find boron in the crust of the Earth, this is what you're going to find, 80 to 20. This is important because we take percentage into account when we calculate the average mass. So what would be the average mass? If 80% of a room full of people weighed 11 and 20% of a room full of people weighed 10, how do you take the average mass? That's what we're going to talk about. The periodic table shows its average atomic mass. Here is boron. So it isn't exactly 11 or it isn't exactly 10. It's actually 10.81. How did we come up with that average, 10.81? Somewhere between 11 and 10. How did we find that? The bottom number is the average atomic mass for the boron. It's given in atomic mass units. So this is kind of a fake number. Typically the unit for mass would be pounds or kilograms or grams, but in this case we use atomic mass units, and so it's based on the number of protons and neutrons. That's what we mean by atomic mass units. To calculate the average mass, we need the mass of each isotope and the percent of atoms in each isotope. So now we're going to do a little bit of math. How do we calculate an average? So here's 80%. We make a table. 80% has a mass of 11.01. 20% has a mass of 10.01. Where does this 01 come from? Well, it turns out that the mass of protons and neutrons isn't it exactly equal to 1. There's a little bit of additional mass. But let's ignore that. Let's just say it's 11 and 10. Okay. But if you add them together, 11 plus 10 divided by 2 does not equal 10.8. The mass is not equal to 10. 11 plus 10, that's 21. 21 divided by 2, 10.5. So where does this 0.8 come from? Well, we have to take account for the relative amounts using the percentage. So 0.8 times 11 plus 0.2 times 10, that does equal 10.81. Okay, so this is how we do it mathematically. You can also think of this as, instead of using percent, you could just take 100, take 100 atoms. Out of 100 atoms, how many will have a mass of 11? Well, 80 of them. So 80 of the atoms has a mass of 11. What's the total mass of the 80? You multiply 80 times 11. What's the mass of the total mass of the boron 10? Well, there's 20 of them, so 20 times 10. Add them together and divide by the total, which is 100. Same idea. Okay, but in this case, we don't use 100, we use 1. So 0.8 plus 0.2 is 1. 0.8 of the atoms are 11. 0.2 of the atoms are 10. Multiply, add it together. This gives part of the average atomic mass for each isotope. 8.81 atomic mass units of the mass comes from the boron 11, and the rest comes from the boron 10. Adding the two parts together gives the average atomic mass. The average atomic mass is weighted according to the amount of each isotope. Okay, now this is one way to get an average. There's other ways to get an average. But you should be familiar with these methods of obtaining an average. In this method, we use percentages. Right? Another way to do it is just to count up the total, right? The mass, what's your mass? Add it to the next person's mass, to the next person's mass. Just add up the total mass of the room and just divide by the total. That's another way to do it. Magnesium has 3 isotopes. Each isotope of magnesium has 12 protons. Okay, so the mass number is the total number of protons and neutrons. We can use this to figure out the number of neutrons. Again, neutrons equals the mass number minus the number of protons. So the isotope magnesium 24, 24 minus 12 is 12. Magnesium 25, 25 minus 12 equals 13 neutrons. And 26 minus 12 equals 14 neutrons. So here are the number of neutrons in each isotope of magnesium. Here are the percentages. The heaviest, I should say the lightest form of magnesium is the most abundant. 78% of the magnesium that you find in the Earth's crust has 12 neutrons. 10% has 13 neutrons, 11% has 14 neutrons. So again, you just multiply the numbers together and add them up, divide by 100, since percent is based on 100. Again, they've already taken out the 100 by just making it a decimal. Add up 18.95 plus 2.49 plus 2.86, and you get the atomic mass. All atoms are isotopes. We just use the term when we need to tell the difference between atoms of the same element with different numbers of neutrons. All atoms are isotopes. In fact, hydrogen has several different isotopes. For chemical reactions, this is not important because chemical reactions depend on the number of electrons, not the number of neutrons. For nuclear reactions, however, it's important to consider the mass of the atom. The number of neutrons will determine how stable the nucleus is. If we do need to refer to a specific isotope, we use a special isotope symbol shown below. Again, this is kind of a review. How do we determine how do we experimentally, how do we determine whether it's one isotope or the other isotope? Well, they weigh different masses, so we can base the mass, we can design some kind of apparatus or some kind of experiment that will cause the different masses to settle out. And that's how we do it. Heavier things tend to go to the bottom because of the force of gravity. Lighter things tend to go to the top. So if you can get a pure form of boron, you can actually use this principle to separate the isotopes and determine the percentage compositions. Okay, so that's the tutorial. I'm going to end the video right now, and I'll end it with some country western music. Cool, huh? So here we go. I'll see you in the next video. In the next video, we're going to go over the problem set for isotopes. Chemthink. Bye-bye.
Sorry, I was